Okay, I think that's working. All right, well, it's been a while. You know, I'm a little bit rusty. It's been about 2 weeks since we've had a normal lecture, and so we'll get ourselves back into it. I guess I should talk a little bit about the midterm. I don't remember the numbers off the top of my head. I think our average in this class was about 28. I think that was about somewhere around there, which is out of 50, which is good. If it had been 20 out of 100, that'd be really worrisome. But 28 out of 50, it's actually not that unusual in line with historical standards. Some people did very, very well. Other people did not do so well. I don't know how the department as a whole did, so I don't know how I can say, well, let's compare it to everybody else. As a general rule of thumb, because we have so many students, roughly what happens in this section is a pretty good indicator of what happens for the department as a whole. Now, if you've gone to Blackboard, you will see that there's a discussion about how to interpret where you're at right now. So I went through, because we have to do midterm grades, and I went through and I said, okay, let's look at your best 5 quizzes, your 2 in-class tests, and your departmental midterm, and use that to generate a score, which would roughly be something that we would use if we had to give a grade. And that was generated. Everybody has access to see what their score is, and you have a rough idea of how you're doing in the class as a whole. That being said, I know a lot of people are very frustrated right now. I understand that. It's natural to be frustrated in mathematics. That's actually the state of a mathematician, is frustration. And there is some seriousness to that. Is to be a mathematician, to survive, you have to be constantly frustrated. That's a story for a different day. I do want to say no one has actually failed the class yet. We are about to take a dramatic right turn. Starting in today's lecture, we're going to move to a topic which is completely different from what we've done before. For some of you, that might be a very good thing. It might say, okay, I really struggled when I did these applications and these advanced techniques of integration, but boy, I love these series and sequences, and it's awesome. I'm going to have fun with the rest of the class. So your grade can go up. On the other hand, some of you did fantastic, and your grade could go down if you don't keep that up. Nothing has been set in stone, is what I want to say. Things can change, sometimes somewhat dramatically. So just, if you're doing well so far, work hard, as I have been. If you haven't been doing well, work harder. And I don't want to say it just comes down to how much time you spend. You know, you want to spend it in a smart way. You know, try to find what works for you. If you need help, seek out help. There's office hours with the TAs, and you know, they feel kind of lonely. They're getting jealous when they hear I have so many people coming to my office hours and they only have a handful. They want you to visit them. They're smart people, and you might find that you learn better talking to them than you do from me. All right, any questions before we begin our new topic? Any concerns you want me to address? All right, as far as the tests go, you will get those back tomorrow in recitation. Solutions will be posted sometime later this week, either Tuesday or Wednesday. They haven't been posted yet because there are still a few people who are taking makeups, and we want them to be done before we post the solutions to the actual exam. So I encourage you to take a look and to see what happened. And I guess with that, we can get started. So I don't have a from last time slide. So this is from last semester. Now, this perhaps is a bit of an indicator about where we're going to go today. So last semester we talked about limits, and we had this great notion. What does it mean to say what a limit is? Well, limits ask a very simple fundamental question. We have this function f of x. We're trying to understand its behavior as we're approaching some value. So in other words, for example, we're saying, does f of x get close to L as x gets close to A? What we're really trying to ask is the question, look, I'm not really sure what happens at A. For some mysterious reason, I don't know what's happening there. And I want to ask, well, what should it be? So that's what limits are. What should it be? And well, how do I decide that? And the answer is, I look at what's happening nearby. All right, so if you go through this definition, it sounds very confusing, but if you realize, well, what am I trying to say? I'm trying to say that as long as my input is close, that's this first statement, the distance between x and a, and whenever you see an absolute value, you should think that's a measurement of distance. Absolute value measures distance. How far am I from a? If that's less than delta, then my output is very close. All right, what does that mean? Well, the distance between my function and what I think the answer should be is small. I can make it very small by making my input very close. Now that was when we had functions. So what's going to happen now? Well, we're going to move to a new idea, which is we're going to deal with sequences. Now, a sequence is a fairly simple idea. A sequence is the following. It's a list of numbers. And usually when we're talking about sequences, we'll talk about infinite lists. So I have this long list of numbers where I start somewhere. I call it a sub k. Usually we choose 0 or 1. A0, A1, A2, or maybe A1, A2. Where we start doesn't really matter. It's just a choice and it's a convention. The book does almost everything with its sequences starting with k equals 1. So A1, A2, so forth and so on. I think it's better to start with 0, A0, A1, A2, so on. But the truth is it doesn't matter where we start. It's what you need. Because the start is not important. And we'll talk about that more as we go on. The start is not important. Now, so I have this long list of numbers, and usually the way we can think about it is we can say, well, what's really happening here? Well, what's happening here is that I say the nth term in my sequence a sub n is really some function evaluated at n, or it's the nth term of this function. So in other words, I can think about sequences as really somehow representing functions. And one notation that you'll often see is you say, well, there's some function which depends on n, and then I'm going to take my sequence from k to infinity. So you've seen this notation before when we've done evaluations of things like integrals, where it's like, well, from a start to a stop. This is just saying from starting from k going to infinity. So let's see some really simple examples of sequences we might see out in the wild. So -1 to the n, as n goes from 0 to infinity. Well, what does that sequence look like? Well, it starts at n equals 0. -1 to the 0 is? It's 1. -1 to the 1 is -1. And it turns out that this sequence, it's not very hard. It just alternates. -1 plus 1, -1 plus 1, dot, dot, dot. And by the way, we are going to see a lot of the dot, dot, dot in the next few weeks. The dot, dot, dot is a way to say, and the pattern continues. And you keep going. So that's what you need. Whenever you see a dot, 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 read it to say, the pattern continues. Now here is a different sequence. 2n, starting with 3, going to infinity. Well, what's my first term? 6, because I'm starting with n equals 3. What's my next term? 8. So wherever you start, and then you just keep going to the next number. Add 1. So 3, then 4. Next one? 10. Next one? 12. Yeah, these are the even numbers starting at 2n. Starting at 6. Here's a different sequence. 2n plus 6 from n equals 0 to infinity. What's the first term? 6. What's the second term? It's 8. The next one? 10. Then? Yeah. Notice something. What can you say about these two? They're actually the same. Now you might say, well, wait a second, they look different because this one has a plus 6 and that one doesn't. Well, what's happening here is I'm shifting where I start my index. So by shifting where my index starts, I can get a new sequence, which looks identical, by making appropriate changes to the function. This ability to shift, by the way, will be important. And if you go on and take differential equations, it'll be very important, very important. Well, what if I had 2n starting from 0? What would that start as? Yeah, it starts at 0, 2, 4, and so forth and so on. All right, now it could be more interesting. 2 to the n over n squared from n equals 1 to infinity. What's your first term? 2, which is 2 over 1. What's your second term? It's 1. Okay, so it looks like our sequence is getting smaller. Well, because we started with 2 and then we were at 1. What's the next one? 8/9. Aha! Again, smaller. Well, what's the behavior? Well, the thing is, don't be misled by the first couple terms. What's the next one going to be? Well, the next one, back up to 1. After that, 32 over 25, bigger than 1. After that, oh boy, 64 over 36. Well, yeah, we can just write it that. You could also, of course, divide out by a 4, get that as 16 over 9. In fact, as n goes off to infinity, 2 to the n grows a lot faster than n squared. So it's nice to sort of get an intuition about how do things grow in relationship to one another. And there's a few basic rules. Exponentials grow very fast. So if you have any number bigger than 1 to the n power, it grows very fast, faster than any polynomial. So 2 to the n beats n squared. Now you might say, so exponentials will always win the race. Well, it depends who they're running against. There's something which is even faster than exponentials, something super exponential. Okay, so what are the kind of things you might want to do with sequences? Well, one thing we might want to know is what is the long-term behavior? So in other words, what happens to these as we go off to infinity? Now, most of these are pretty straightforward, and we could prove these. But let's just go ahead and say what happens. So here we go. We were going to say that a sequence a sub n is approaching a value. So in other words, as n is going to infinity, my sequence approaches a value called L. When is that true? Well, we think about limits. We want to make sure that if our input was close, then our output was close. Now here our outputs are really the terms in the sequence a sub n. So we want to make sure that our a sub n are getting close to L. And when we say close to L, all the ones near infinity towards the back. Well, how do you get near infinity? Well, the answer is you just say, well, you're very large. Okay, so here we go. Here's the definition. For any epsilon you pick, there's a capital N. That's a big N. Usually it tends to be very big. And I will say that implicitly, when we write this, there's a capital N which depends on epsilon. So in other words, your choice of N depends on how close you want epsilon to be. So there's some capital N, so that if you're very large, N is bigger than capital N, then a sub n minus L is less than epsilon. I put here n is close to infinity. Well, of course, no number is close to infinity. All of them are very far away. But the intuition says the bigger you are, the closer you should be to infinity. So that's our intuition. Now, what if there is no such L? Okay, in that case we say that the sequence diverges. And it's possible no such L can exist. So here's a very simple example. Let's look at the sequence 1 over n. I claim that if we look at this sequence 1 over n, starting with n equals 1 and going on, that it goes to 0. Well, we should probably check. The first term is 1, then 1/2, then 1/3, then 1/4. Well, it would appear, as we write these down, that these numbers are getting smaller. So intuitively, at least at the front, it seems like that's true. Okay, so now let's go through and use the definition. And in case you're nervous, we're not going to test you on using the definition, but it's good to understand that it exists and how it works. Because even if you don't use it explicitly, it's good to understand how it works implicitly. So what do I need to show? Well, I have to show for any epsilon, there's a big N. Okay, so take some epsilon greater than 0. Okay, let's just make an observation. What do we want? So we'll do a little side note. This is what we want. Well, we want that a sub n minus 0, or this is really, I should say, this is our what we think L should be, to be less than epsilon. Well, a sub n I happen to know is 1 over n. So I want 1 over n to be less than epsilon. Well, if I want 1 over n to be less than epsilon, I can flip it and say I want n to be, so I'm taking 1 over n and I'm flipping it to be n over 1. If I flip, what happens to the inequality? Instead of less than, it's greater than. And on the other side, I flipped out 1 over epsilon. Now, here's the thing. This 1 over epsilon, this is our new bound. That's our capital N. Aha! So now we figured it out. So we knew what we wanted. We figured out what needed to be true. So take epsilon bigger than 0 and choose capital N, capital N to be 1 over epsilon. Then, what's the case? If n is bigger than capital N, we have a sub n minus 0 is less than epsilon. And that's the whole argument. It's a very simple limit, so it's not terribly surprising. Okay, let's do one a little bit more interesting. All right. So here's a sequence. Suppose I have a sub n, and it's 1 plus negative 1 to the n over 2. And starting with n equals 0, 1, 2, so forth and so on. What can we say about the limit as n goes to infinity of a sub n? Well, let's build up some intuition. Let's see what's happening. If I plug in 0, what will I have? Well, plugging in 0, what do I get? I get 1 plus negative 1 to the 0 over 2, which simplifies to 1. If I plug in 1, 1 plus negative 1 to the 1 over 2, which will become 1 plus negative 1, which is 0 over 2, which is 0. Okay, what's my next term? 1 plus negative 1 squared over 2. It's 1. What's my next term? 0. What's my next term? 1. Then 0. Now you might notice there's a definite kind of pattern here. All right, now, question. What is happening to this sequence? 1, 0, 1, 0, 1, 0, 1, 0. In the limit, what does it go to as you go to infinity? Now, there's usually 4 guesses. I'll tell you what most people would guess. A lot of people would say, well, it's 1, or it's 0, or we should average. Because, it's like half the time it's 1, half the time it's 0. So it's about a half as you go to infinity. There's a 4th one. So what's the 4th one? It diverges. Now, which one is correct? The diverges is correct. Now, why is that correct? Well, okay, so one way you can think about limits, or you can think about them as sort of this function you're evaluating as you're plugging in n. Another way you can think of it is as points on the line. So I take my line, and I happen to have 2 special points, 0 and 1. So here's 0, here's 1. And what this sequence is doing is it's alternating. So it's first at 1, then it's at 0. And then it's at 1, then it's at 0. So it's going back and forth. Now the problem here is what needs to happen. In order for the limit to exist, you have to get near a point, but more importantly than you have to get near a point, you have to stay near a point. So if I put back up the definition of limit for a moment, you'll notice here it says eventually, so this capital N is saying eventually, you're going to stay close. So it's not that you get close infinitely often, it's that eventually you will stay close. That's what a limit is. You're staying close from some point onwards. So there's a difference between getting close and staying close. All right. So the problem here is, no matter how generous I am, maybe I'm a fairly generous person, and I say, look, how often do I stay in this small window around 0? And the answer is, I never stay. I always jump in and out, in and out, in and out. It's like these bad relationships you have. You're off again, you're on again. So you have to stick. You have to stick. Now, we should compare that to a sequence we just talked about a little while ago, which was the sequence where we had 1 over n. Now, for 1 over n, what happened? Well, what happened was we started at 1, then we went to a half, then a third, then a fourth, then a fifth. See, what's happening is, if you look around 0, eventually I will stay nearby. I get in, and then I'm always going to stay in. So that's why 1 over n went to 0, but this sequence 0, 1, 0, 1 does not go to anything. By the way, I'm sure you can find videos on YouTube that say, yes, this sequence 0, 1, 0, 1, the answer is a half. Well, that's because they don't understand mathematics. Don't trust them. Don't trust them. Those are alternative facts when it comes to sequences. You should not believe that. All right. Now, with limits, there's a lot of good intuitive things which are true. We did this when we did limits for functions. We still have them for limits of sequences. So if you have a nice sequence, so a sequence which converges, suppose a sub n is a sequence and it converges to some value a. B sub n is another sequence, it converges to some value b. And we want to say, well, can we do things by combining the sequences? And the answer is yes. We can say, well, the limit as n goes to infinity of a sub n plus b sub n is a plus b. What I'm really saying here is if I have something where my pieces converge individually, then I can break it apart and say, look, let me work on each piece one at a time. Now, you have to be careful here. It's possible that a sub n doesn't converge, a sub n doesn't converge, b sub n doesn't converge, but a sub n plus b sub n does converge. So you want to be careful. You want to be careful. We can give an example of that if you want. Do you want to see such a thing? I don't know. Yeah? Okay. All right. All right. Well, I happen to have a piece of paper here. Let's see. I hope I get this right, otherwise this will be embarrassing. Let's suppose my sequence a sub n. It's a very simple sequence. I will make it square root of n squared plus 4n. And I'll go, of course, from 1 to infinity. And b sub n, I will make this be my sequence minus n, as n goes from 1 to infinity. Now, maybe it's easier to notice with the b sub n what's happening here. Well, this is -1, -2, -3, -4. What's happening to that? We don't have a really good name for that, but I think we can all say what that is doing. What's happening? It's going to negative infinity. So we could say it's diverging to minus infinity. Okay, so b sub n diverges to negative infinity. Similarly, if you do a sub n, you'll see that a sub n, I won't go through the details, diverges to plus infinity. Now, suppose I want to look at the limit as n goes to infinity of a sub n plus b sub n, so square root n squared plus 4n minus n. Well, look, a sub n doesn't converge. B sub n doesn't converge. So I can't split them up. Now you might say, well, why can't you? Well, if I split them up, I would say this would equal infinity minus infinity. But what's wrong with infinity minus infinity? It's indefinite. Another word is it's ambiguous. It's nothing. Or rather, it's everything. Because it really can be anything you want it to be. So you don't get a good answer that way. So can we evaluate the limit as n goes to infinity of root n squared plus 4n minus 4? And how do we do it? Now it's like, okay, what's my cool calculus tool? I hate to tell you, it's not a cool calculus tool. It's a cool algebra tool. Conjugate, yes. Okay, so what I can do is to evaluate the limit, I'll rewrite the limit. It's the same thing with integrals. To evaluate the integral, we rewrite the integral to something that's easier for us to work with. Now what's the conjugate? Well, it'd be root n squared plus 4n plus n. I'm going to multiply on top and the bottom. And can I skip the intermediate step? Just jump ahead to what happens. If you multiply by the conjugate, you will get on the top n squared plus 4n, because you'll square that, minus n squared over root n squared plus 4n plus n. Now, at this point, we use our tools of elimination. We can cancel off an n squared. We have infinity over infinity, though, because 4n keeps getting bigger and bigger and bigger, goes off to infinity. Downstairs keeps getting bigger and bigger and bigger, going off to infinity. What's our next cool algebra thing to do? Well, we could do L'Hopital, but let's do algebra right now. L'Hopital can work. Maybe. Yeah, it could work. But there's some simple algebra that can be done. And there's a nice philosophy here, too, which is to say, what's really driving the growth? So upstairs, what's really making it get big? I know it sounds like a silly question, and you're like, it's obviously that thing, and it can't be so obvious. What's the obvious answer? What's making it get big upstairs? The n. The n is making it get big upstairs. So what I can do is I can say, let me divide out by what's making it get big. So I multiply top and bottom by 1 over n. And if I do that, I see that I'll have limit as n goes to infinity. Upstairs, I'll have 4n times 1 over n is 4. Downstairs, if I multiply the 1 over n, well, the plus n times 1 over n is easy. That's plus 1. And I can bring the 1 over n inside the square root. And if I do that, I'll get square root of 1 plus 4 over n. So I'm skipping a few algebra steps. If you're confused, turn to your neighbor and copy off their notes. No. Don't. Come talk to me. Now, finally, we say, okay, what happens as n goes to infinity? Well, there's only one n, and that's driving that term down to 0. So what's the answer? It's 2. So here we see, even though a sub n and b sub n individually don't converge, their sum does. So this is just be careful. Sometimes when you have two wrongs, it does make a right. So two things which don't converge can combine to converge. So just be careful. Similarly, you have the limit k times a sub n. That'll go to k times a. Limit of a sub n times b sub n is a times b. And as long as b is not 0, you can even take the ratio. And this is mostly a way of saying, look, we can break things up in nice ways. All right. Aha.
Does the same rule apply to this where all of these, or if they both necessarily may not?
Yeah. So for any one of these, it can be the case that individually things don't converge, but collectively they do. There is even, you might say, well, what about this second one? Surely the second one, it has to be the case that in order for it to converge, that a sub n has to converge. You can actually cheat a little bit. What if k were 0? If k were 0, 0 times a sub n becomes 0, which definitely converges. And so you have to take things with, just be careful. There's a general rule of thumb when it comes to limits. Anything that seems reasonable probably isn't true. So you just have to think, okay, what's unreasonable? That might be the case. That might be the case. All right. One other fun fact. We have the sandwich, or the squeeze, or as I like to call it, the squish, which says what happens. So suppose you have some sequences, AN, BN, and CN. And AN, it has some behavior, and CN has some behavior. These are the ones that bound. So AN and CN are bounding BN above and below. But it just so happens that AN and CN are moving towards each other. So as n goes to infinity, they both approach L. Well, the thing is, BN is caught in the middle. And since AN and CN both get close to L, it has no choice. It too must also get close to L. So here's a nice example. Suppose I ask you what's the limit as n goes to infinity of cosine of n divided by n. Now, the thing is, cosine of n doesn't behave very nicely. It jumps all over the place, goes up and down in sort of somewhat erratic ways. However, what's something that we can say for sure about cosine of n? It's between -1 and 1. Cosine is bounded. This is a sneaky way for us to make complicated expressions which really aren't that complicated. So what I can say is that cosine of n over n, it's less than or equal to 1 over n, and it's bigger than or equal to minus 1 over n. So I can think of this cosine n over n as caught in the middle between 1 over n, that's my Cn, and -1 over n, that's my a sub n. But we know what happens to 1 over n. What does happen to 1 over n as you go to infinity? Goes to 0. Well, what happens to -1 over n as you go to infinity? Well, goes to -0, right? Oh, well, which is the same as 0. And why do we know that? Well, we know that because we know what happens to 1 over n, and we have this nice fact that I can multiply by a constant. So that's why I said -0. Okay, well, if that goes to 0, that goes to 0, and this is stuck in the middle, what can we conclude? Also has to go to 0 by squeezing. All right. So there's that fact. Now, I should mention, someone previously had mentioned the L'Hopital. But we do have to be a little bit careful. Okay. So here's a fun fact. If we have a nice function, and nice in calculus means you can take a derivative. If we have a nice function, and it's the case that a sub n is f of n, then if the limit of the function f of x goes to L, then the sequence goes to L. All right. Now, technically, to be nice in this sense, we really just need continuous. But okay, so we're nice. So we have a function. So what are we saying? Well, our function here, it's collecting what's happening on our points. Now, again, as a word of warning, just because something sounds reasonable doesn't mean it's true. So notice I said if the limit of the function f of x goes to L, then the limit of the sequence a sub n goes to L. Is the converse true? If the limit of the sequence goes to L, is it the case that the function must go to L? What do you think? Well, it sounds like it might be reasonable, so it's probably not true. And you're right, it's not true. Now, how do we know? Well, we'll do an example. Here's a function, a very simple function, sine of pi x. Now, let's ask two questions. We're going to let a sub n equal f of n. And so we're going to ask, what's the limit, first, as x goes to infinity, of f of x? Well, that's the limit as x goes to infinity of sine of pi x. Well, what does that go to? as you go to infinity? Well, it goes between negative 1 and 1. Sine does, but what does the limit do? Yeah, doesn't converge. Doesn't converge, or diverges. So the limit doesn't converge. Very sad. Very sad. All right. Well, let's think about a sub n. What is the sequence a sub n? Well, what's the first term? Let's start with n equals 1. That's sine of pi. What's another name for sine of pi? 0. N equals 2 is sine of 2 pi, which is what? 0. N equals 3 is sine of 3 pi, which is 0. N equals 4 is sine of 4 pi, which is 0. You might notice there's a pattern here. In fact, that pattern continues. Does this sequence converge? The answer is yes. Where does it converge to? 0. So the thing is that even though the function can diverge, what can happen is, based on where you're sampling, you might have sampled in a very nice way, so the sequence will converge. So just be careful. Just be careful. However, that being said, now we can say things. Why do we want to make this observation that if we have a nice differentiable function and a sub n is f of n, then I can figure out the limit of the sequence by looking at the limit of the function? Well, the problem is sequences don't have derivatives because sequences are discrete. Discrete means they're separate individual terms. They don't interact with each other. Functions, though, are continuous. And you have this nice continuum. And then you have derivatives and you have L'Hopital's rule. So now we can start looking at things. For example, f of x is x squared over e to the x. Now earlier we looked at x squared over 2 to the x. I'm using e to the x because then I don't have to worry about taking the derivative of 2 to the x, which we can. It just, I don't like having lots of log 2's floating around. So what's the point? Well, the point here is for us to understand this limit, I can look at the limit as I go to infinity of x squared over e to the x. Well, what does that do? Well, sure, it does approach 0, but what does it first do?
This converges, and you know what to do for the other one that we're trying to solve for.
Well, it's true that if this converges to something, then we definitely know what to say about the a sub n. So as you go to infinity, the top is infinity and the bottom is infinity. It's infinity over infinity, which is undefined, ambiguous. So when we see such a thing, what do we do? What do we do? Yeah, we can apply L'Hopital's rule. All right, so this is the limit as we go to infinity of 2x over e to the x, which is still undefined, still infinity over infinity. So what do we do with that? We'll apply L'Hopital's rule again. Well, what do we get? Well, we'll get a limit as we go to infinity of 2 over e to the x. What does that do? That goes to 0. So now as a continuous function, x squared over e to the x goes to 0. So then once we're sampling, which is what really the a sub n is doing, is really you're sampling what the function is. Now I say the word sampling because some of you will actually see this word again later on in your life in future classes. So when you think of the word sampling, it's just like, oh, I'm just picking up some individual points to try to understand behavior. So a sub n does what? Goes to 0. Goes to 0. And this shows you that exponential can beat polynomial. All right, here we go. A few basic sequences. These are things that you should know. So when you take the limit as n goes to the infinity of the nth root of n, that will always go to 1. And that's not a very hard thing to show. Basically what you do is you think about what happens to x to the 1 over x, and then you apply logs, take L'Hopital's, and it works out nicely. And I'll skip the details. if you have a small x, and small here, we say small means close to 0, in particular, the absolute value of x is less than 1, then when you go to infinity x to the n, that's going to get small. So a very small number, you keep multiplying, it's shrinking, 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 shrinking. And we have a nice name for this, which we'll talk about. This is called geometric. And geometric is one of the most important things that we're going to look at. If you take 1 plus x over n raised to the nth power, and the limit as n goes to infinity, this is e to the x. And this is true regardless of what x you pick. X could be as large or as small as you want. This is another nice application of the L'Hopital's rule. And depending upon who you had for Calc 1, you would have seen something like this in your class. And the last one here is you have the limit as n goes to infinity of x to the n over a very excited n. People would say, n! Ah! Now, that's not what it really means when you see an exclamation mark. It's not like this is like, oh yeah, I'm an n, woo! No, it's saying n factorial, n factorial. What is factorial? Well, by convention, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. In general, the way you get n factorial is you multiply n times n minus 1 times n minus 2, so forth and so on down to 1. So you're essentially multiplying the first n numbers together when you get n factorial. And the reason why 0 factorial is 1, well, that's the empty product, and that's an interesting discussion which will lead us somewhat astray. Now, what's the moral? The moral about this is that factorials grow very quickly. They beat exponential. We already saw that exponentials beat out polynomials. But factorials grow even faster. Factorials are very, very fast. And of course, there's things which are even faster than factorials. There's a whole range of different numbers out there. Now, for those of you who like your very fancy calculators, and I know a lot of you pulled out your very fancy calculators when you took the test, you might try to see what happens when you punch in 1/2 factorial. Because you might say, 1/2 factorial, there is no such thing. But your calculator, if it's a good one, will say that there is. And it'll give you a really strange number. And if you try it, take that number and square it and multiply it by 4, and then you'll get a really strange number. And why do you get that number? That's a great question. Let's see, did anybody try it? Sorry, what? You have a really nice calculator, yes. So Wolfram Alpha knows it. Yeah. Well, yeah, so 1/2 factorial is the square root of pi divided by 2. And you're probably thinking, that doesn't sound right. But it's true. It works out. That's a great discussion to have once you get a little bit further along. Next semester. Okay. Now, one type of sequence that is very important, and again shows up often, is the recursive sequence. Now, recurse here says, look at what you've already done. Look at your previous terms and use that to make a decision about what your next term should be. So whenever you hear the word recursion, it just says, look at what you've done to this point so far. That information feeds into your next data point. So for instance, suppose I had a0 is 1, and then I said to find my next term, I take n multiplied by my previous term. So for instance, I could say that a1 is 1 times a0, which is 1, because a0 is 1. a2 is 2 times a1. So notice I put in n equals 2. So a sub 2 is 2 times a sub 2 minus 1, which is 1. Well, 2 times a1 would give me 2. a3 is 3 times a2. Well, that's 3 times 2, which is 6. What's a4? 4 times a3, which is what? I think somebody said it. 24. Do you see the pattern yet? Next one is $120. Does anyone see the pattern yet? I hope so, because I'm going to run out of numbers I can multiply. 720. Well, I won't run out of numbers to multiply, just ones that I can do in my head. Next one is 5,040. Has anyone seen what the pattern is yet? Yes, notice that this 2 is really 2 times 1. 6 is really 3 times 2 times 1. 24 is 4 times 3 times 2 times 1. 5 times 4 times 3 times 2 times 1. And in general, what we're seeing here is that these are factorial. So you can define a factorial recursively in this manner. All right, let's see. All right, that's kind of a fun one. That's kind of a fun one. Let's see, how much fun do we have? Let's do this one. This one's nice. So let's do something slightly different. So this, last time we said multiply by n. This time we say add n. So b0 was 0. b1, I'm going to take my previous term and add 1. 1. b2, 1 plus 2, which is 3. b3 will be b2 plus 3, which is 6. b4 will be b3 plus 4, which is 10. b5 will be b4 plus 5, which is 15. Do you see any patterns yet?
Each number is one more than the difference between the previous two numbers.
Whoa. Well, that's true. That's true. That's true. Now, in case you're wondering whether these numbers are interesting, the answer is, of course, yes. There's, in fact, a whole website devoted to interesting numbers called the Online Encyclopedia of Integer Sequences. And these numbers right here are some of the more interesting numbers. And you might wonder why I'm drawing a lot of dots here. Well, there's a moral to this. These numbers right here are what are called the triangular numbers. And what I can do is I can grab a piece of paper and I can just ask a question. How many dots do you see? Now how many? 3. 1 plus 2, 3. Now how many? 6. And 10, 15, 21, 28, and so forth and so on. So these numbers right here are called the triangular numbers. And so if you ever hear anybody talk about the triangular numbers, they're talking about these numbers. And there's a formula for it. It is equal to n plus 1 times n over 2. And if I had time, I would prove that. But we are almost out of time, and I just want to make a statement here. Because we're going to talk about convergence of sequences, and next time we're going to talk about series. And there's something that's important to say, and I want to say it very explicitly, and I want to put it up on the screen. When we talk about convergence, we don't care what happens at the beginning. Convergence questions never have anything to do with how you start. The first 100 term, the first 1,000 terms, the first billion terms, unimportant. Convergence always happens at the tail. And when we talk about the tail, that is what's happening as you get close to infinity. And that's where we're going to have to focus our energy. So be careful. It's easy to be misled by what happens at the start. It's what happens at the end that counts. And to make sure we get it right, that's why we have math. And math is good. And that is a good place for us to stop. And we'll see you on Wednesday. Have a good day.